Alright, welcome everyone to this final video on two-component phase diagrams. This video we're going to talk about distillation or fractional distillation, right? And so distillation, right, itself is, so distillation by itself is just you have some liquid, some mixture, some solution, right? You boil off, say the solvent, you then try to collect and condense that solvent, right? Like if you're trying to purify water out in the woods or something like that, right? If you don't have a source of pure drinking water, right, you could boil the water, right? Try to capture the vapor, right, on a lid of your container, some other thing, right, to have it condense on that thing. It condenses and then you have it drip to some other container, right? And then you'll get pure water, right? And what will be left in the mixture is all the non-volatile crap that you don't want to be drinking, right? Well, fractional distillation is that same process of distillation where you boil something off, you condense it back down, right? But then you do it multiple times, okay? So you keep on boiling and condensing things over and over and over, okay? And this way you can separate liquids of different volatilities, okay? And how they separate is based off of their difference in volatilities and boiling points, okay? So we previously talked about phase diagrams of pressure versus mole composition, okay? You can create a similar phase diagram of temperature versus mole composition, okay? We're not going to go and derive those formulas, okay? But you can derive that and you get a very similar phase diagram, okay? Now, in this case, when you have temperature versus mole composition, okay, it looks fairly similar to the liquid versus, or the pressure versus mole composition, right? But just notice that the vapor phase, right, in the top part of the diagram is what's the stable phase, right? And the liquid phase is what is the stable phase at the lower part of the diagram, right? At room temperatures, the liquid is more stable than the vapor, right? Should be expected, okay? So, and we're assuming for this process, right, the pressure is remaining constant, okay? Right, again, the boundaries, right, are giving us the equilibrium, temperatures between these different phases and things like that, right? And then again, between the lines, you have two phases in equilibrium, okay? So same type of thing as pressure versus mole fraction phase diagrams in the previous video, okay? But here we just have temperature. Okay? So let's consider, right, that we heat some liquid, right, right at point A1 till it reaches its boiling temperature, right, and starts boiling off, okay? Well, when A1 starts boiling off, right, the temperature is now staying constant, and now I'm converting my liquid phase to my gas phase, right? So I'm at, right, so I have some liquid, right, which has some mole fraction of A in that liquid phase, right? I start boiling it off to the vapor phase, right? Well, when it reaches the vapor phase, it has some mole fraction of A in that vapor phase, right? And they are different from each other, okay? Right? And again, simple distillation is you then just take out this, gas, and you condense it down, and that is, your final product, right? And again, this works great for separating non-volatile solutes, okay, or solids, right, from your liquid, but not so much when you have two liquids, right? Because in this example here, right, I now have Y of A is, right, a mixture still of A and B, right, and you're not really getting pure A back. But what I can do is now, if I have this mixture Y of A, right, so I boiled off my liquid, and now I have it in this composition Y of A, right? I have some amount of gas phase that's at this composition Y of A, right, as I'm boiling it off, right? If I then cool that vapor, right, off, right, it's going to condense down to the liquid phase. Well, when it condenses down to the liquid phase, right, as I'm cooling it off, it will eventually, as it condenses down to liquid, start boiling again. But when it boils, it's now going to release a vapor, okay, that is at a higher composition. I'm going to call this YA prime, right, of A, okay? And then I can repeat this process, condense it and boil it off, and condense it and boil it off, right? And so again, how you do this, right, is you start boiling your liquid. You have some layer above it where you condense the vapor to a new liquid, and you start boiling off that liquid. And then you have another layer where you condense that and start boiling off and blah, blah, right? And keep on going, okay, until you will eventually reach pure A at, you know, some higher level of this tier, right? For this multi-liquid mixture, right, where you have multiple volatile liquids. And so I can use this fractional distillation where, again, I basically do distillation multiple times in a row in order to purify my liquid A. Okay. Right. Now this can't be done for all types of liquid mixtures. Okay. Now there are things called Isotopes, okay, which are liquid mixtures, right? That at some point the chemical composition in the liquid and the vapor phase are equal to each other. Okay. That's represented by that point I've circled, right? At that point, I can't use distillation to further purify this, okay? Right, so what's represented in this diagram is a high boiling azeotrope, okay? And this can often occur, right, when the interactions between A and B are stronger than they are between A and B and B, okay? Right, so A and B attract each other more than A attracts itself or B attracts itself. Okay. Right, if I consider a high boiling azeotrope, right, let's say we start off at you know, some composition, and I heat this up to A and I start boiling it off, right? I get to A2 prime, right, which is higher in composition A, right? I remove some of that vapor, right? And as I'm blowing it off, right, I can start condensing this down, right? And I will get some pure amount of A as this is boiling off, right? I will get some liquid A that is pure, right? But the problem is right, as I'm boiling off, right, we didn't talk about this in the previous slide, right, but as you're boiling off your liquid, right, and you're getting higher chemical compositions of A, right, the liquid that remains slowly gets to lower compositions of A, right, because that's what's just going to happen, right? If I have more A in the gas phase than I do the liquid phase, right, as I keep on boiling it off and generating more A, more B is being left behind in the liquid phase, and so eventually my liquid's mole fraction, right, is going to get smaller and smaller and smaller, right? The mole fraction of A is going to get smaller in the liquid phase as I'm boiling this off and purifying A, right, for a normal fractional distillation process, okay? And so you'd eventually end up with pure A and pure B and fully separate these two things in an ideal situation, right? But for this high boiling azeotrope, right, I'll be able to purify some A, okay, through this fractional distillation process. But as I'm boiling it off and I get fewer and fewer moles of A in the liquid phase, I eventually reach this point, right, where now the chemical composition in the gas phase or the vapor phase and the liquid phase are equal, and I can no longer do any type of distillation, okay? Right? And if I start off with a mole fraction to the left of this point, right, then I'm just kind of screwed in general, right? Because I get here, I try to boil it off, and I'm actually at like a lower composition and things like that, right? So yeah, so for high boiling azeotrope, I can purify some of A if I'm on the right side of that azeotropic point, okay? But I'm not going to be able to purify all of it, right? Because eventually I will create the composition of my liquid equal to where that azeotropic point is, and then I'm stuck. Then there's low boiling azeotropes, right? If I start off with some high composition of A, right, and I try to boil it off, well, I actually end up at a lower composition of A, right? Y of A is less than X of A, right? And so I actually start getting to a less and less mole fraction of A until I reach this azeotropic point and I get stuck, right? And so right, and so basically I can't separate these things, right? I might be able to purify, right? If I'm to the right of here, I might be able to purify the liquid a little bit, right? Because as I'm boiling off A, right? Right, the mole fraction here is less than of A in the gas phase than is in the liquid phase, which means I'm boiling off more B than A. So as I'm doing this, I am making my liquid more pure in A, and it is going to the right. But I'm not really going to be able to kind of fully purify my liquid by doing this process, right? So again, this low boiling azeotrope also can't fully separate these things. Okay? And these things occur typically when the interactions between A and B are much stronger than those between A and B, right? And then the normal fractional distillation process we talked about is when the intermolecular forces between AB, and BB are fairly similar, right? When you're dealing with a more ideal type solution compared to some real solutions.